Okay, so the bottom is 0 where? At 1. Is the top 0 at 1? You sure? It is, isn't it? If I plug it in? Yeah, because I'm going to get square root of 25 minus 5, so I'm getting 0 over 0 there. Okay. So we don't know if it's a vertical asymptote or not yet, right? Um, what would we do to find out? By the conjugate of the top, yeah. Okay. So on this one, yeah. So we get, for part B, the limit of square root of all that stuff minus 5 over x minus 1 as x approaches 1 is 0 over 0, right? So we're going to multiply top and bottom by the conjugate of the top. Okay, what's that going to give me? Minus 25, good, right? We're going to do, okay, so on the top, we're going to get x squared plus 2x plus 22 minus 25. Give me thumbs on that. Everybody get why we get that on top? Okay, good. Over a mess on the bottom, but that's okay. It's going to be a self-cleaning mess. This looks really messy, this green factor, but it's actually safe because it does not go to 0 when x goes to 1. Okay, as x goes to 1. So then I got to clean up the top a little bit. If I add like terms, on the top I get x squared plus 2x minus 3, right? Over x minus 1 times square root of x squared plus 2x plus 22 plus 5. Okay. Okay. What next? Factor the top, right? Does that make sense? Do you see why we're doing that? On the top, when we multiplied by that conjugate, we got rid of the square root issue, right? And now we just get a regular old polynomial that I can factor. Okay, so the top then becomes, what's that factor into? X plus 3 times x minus 1. And what's so great about this? What can I do? Good. I cancel the factors that are causing the indeterminacy, the x minus 1s. Good. Okay, and now we've got a limit that we can take. And what do I get? I end up getting what, 4 over 10? Everybody agree? I'm going to get square root of 25 plus 5. Okay. So here's my question then. Did I have a vertical asymptote? I did not. I did not. When I took the limit, it was indeterminate initially, but after I got rid of the indeterminacy, one proved to be, I got a limit that was not a number divided by 0. So it's not a vertical asymptote. There are none. Make sense? What was this instead? How would I describe that discontinuity? What was that? As the ant approached 1, his y value approached 2/5, 4/10, 2/5. The function doesn't exist there, but what must that have been then? If ant's approaching from both sides, both anticipate, what was it? It's a hole, right? Hole in the function. Does that make sense? Because there is a specific place the ant thought he was going to step from both directions. The function just isn't defined there because I can't divide by 0, right? So I have to exclude 1 from the domain, right? We know that our domain is x cannot equal 1. What's going on there? It's not a vertical asymptote. It's just a removable discontinuity, a hole. Okay, give me thumbs on that. Does that make sense? Question? Yeah, right. So we'll do that one, right? So now we got the vertical asymptote part. Now for part A, what do you do with this function when you're trying to take limits at infinity? Okay, so that's when we're taking limits at infinity. This is where we're only going to look at the dominant parts of the top and the bottom, right? So what's the dominant term on the bottom? X, right? As we're approaching the infinities, this is my dominant term on the bottom. What's going to be the dominant part of the top? The x squared, which is inside a square root. So it's really just like the square root of x squared. Okay, does that make sense? So the limit of this function, so this is for part A, the limit of f of x as x approaches plus or minus infinity is equal to the limit of the square root of x squared. What is that? Absolute value of x. That's what's coming out of that guy, right? Divided by x. Okay, make sense? Okay, now let's do one more thing. I'm going to draw an arrow down here. I got to make this thing smaller for a second. So let's go down here and finish this. So I'm going to put an arrow down here. Okay, so oh man, okay, hang on. I gotta make this disappear for just a second. Okay, so now let's look at this. Let's analyze this. Okay, so this is weird, right? I've got the limit of the absolute value of x over x as x approaches plus or minus infinity. Let's take this one step at a time because we really need to consider both of those separately. So what if we're approaching positive infinity? Oh man, this thing is making me play all kinds of games here. Why is it doing that? Oh, I don't know. I'm not going to mess around with this anymore. It's not worth it. Okay, so if we're approaching positive infinity, what is the absolute value of x equal to as I approach positive infinity? Those are positive values, right? So what's the absolute value of x equal to for positive values of x? remember my piecewise function, the absolute value of x equals x whenever x is positive, right? And it equals negative x whenever x is negative, right? Remember that stuff? Okay, so we're approaching positive infinity. So what's the absolute value of x equal to? X. So this is equal to the limit of x over x, which is 1. Okay? Now, as we approach, let's compare that to the limit of absolute value of x over x as x approaches negative infinity. Well, what's the absolute value of x equal to when x is negative? Negative x, right? Absolute value of negative 7 is 7. I've got to take that negative 7 and multiply by negative 1 to make it positive, right? So I get the limit of negative x over x, which is equal to negative 1. So then what's that mean about our answers here? What are my horizontal asymptotes? I've got 2 of them, right? As x approaches positive infinity, my horizontal asymptote is y equals 1. As x approaches negative infinity, I've got the horizontal asymptote y equals negative 1. Okay, because this is like an infinite step function, isn't it? Remember these? Absolute value of x over x just looks like that step function where it just does that, right? Make sense? Okay, good question. A lot of stuff going on in that one. What else? What other ones you run into? Practice test 6. Practice test 1, part 6, right. Okay. Question 4. Okay. Problem 4, you said? Okay. Okay, so there's a couple different possible ones you could get for this. So let's you guys can take your pick. Let me pull them both up and you take your pick which one you want to go through. So that guy.
I could do it, but not. Yeah, that's what. Okay.
Oh, okay, yeah, these are kind of bonus ones.
Well, you just go. What did they do?
Yeah, I'll go over them. It's fine. I'll go over them.
Because I got it wrong and looked back into it, and it said they used like floppy tunnels.
Oh, you guys don't know that. Yeah, that's not.
I was like, okay.
Where did? Okay, yeah. These must be coming from a book that does things in different order. But that's okay. We could do either one of those. Let's just pick one of them. Let's pick. How about we'll pick that one? That looks a little bit harder, so we'll pick this one. Okay. Yeah. Okay, fair enough. Get rid of that guy. Okay. So what do we do? So we technically have 2 special limits. We know that the limit, do you guys remember this? We know that the limit of sine x over x as x approaches 0 is what? 1. And we have one other one that we never use. The limit of 1 minus cosine x over x as x approaches 0 is what? No, 0. Okay, and the reason we never use that one is because we never have to, right? Like I mean, I'm surprised I remembered that one, honestly, because I just always do it using trig identities. So what we could do here instead, we could use that if we want to. So I could rewrite this as the limit of 5 times 1 minus cosine x over 6x squared. And I could break this apart into it's hard to even use this one, honestly. Like it's like that's why I don't teach it, because it's confusing when to use it and how to even use it. So we won't even use that one. Let's do this a different way. Let's just use the top one, which you guys know really well, right? Top one's no big deal. Why can't I just, I don't know why it keeps doing that. Okay, we're just going to use the top piece. In fact, I'm just going to, you guys know that one. I'll just erase the whole thing. Okay, so what do we do to get to that top piece? There's a trig identity here that's hidden. What's the trig identity? We want to get a sine x over an x here if possible. What can I do? When I see a 1 minus cosine x, I'm really thinking there's something I can do here that's always a good idea. What could I multiply that by to use a trig identity that's going to make that a single term instead of 2 in that factor? And this is, keep in mind, this is kind of a bonus. It's only worth like a point out of 100 or something, right? It's not very much. What I would multiply by is 1 plus cosine x over 1 plus cosine x. How come? Okay, and this is just trig stuff, and I get it. I mean, you guys are. That's why I make this stuff a bonus, because you guys are just not. Your trig, honestly, is just not super strong. I mean, but we'll get it strong. We'll just get it. It's just. I mean, and it's not. It's just because you guys haven't used it very much. I mean, you cover in a normal trig class, you just kind of cover the basics of functions and stuff, but you don't really do a of like identity stuff, identity work. And that's normal. I mean, it's not a diss on you guys at all. I'm just saying it's at this point in your math careers, you guys need more practice. The thing is, you're going to get a ton of practice on that stuff this year, so you're going to be fine, right? Okay, but I mean, it's and you'll come to really like trig is so cool. I mean, you can solve so many problems using trig that you can't solve otherwise. I mean, you just got to look at it as a tool. I remember that feeling, like if it's something you're not comfortable with, you dread seeing it. But the best thing to do in life is when you're good at it, what do? You just got to practice it until you get better at it, right? And you'll all be doing a lot of trig stuff in your futures, I promise you. So we're just going to get better at it. Okay. Why did I do this? I did this because what do I get on the top? What do I get on the top when I multiply straight across? Yeah, good, because when I multiply those things together, I've got my 5 on top, and then 1 minus cosine x times 1 plus cosine x. Look at that pattern. That's the conjugate product pattern, right? You guys remember that. That's just saying a plus b times its conjugate, a minus b, is always what? A squared minus b squared, right? So we're just using that same pattern here. So on the top, we're going to get a squared, which is 1, minus b squared, which is cosine squared x. On the bottom, we just get a bunch of stuff. I just get 6x squared times the quantity 1 plus cosine x. Okay, well, what is 1 minus cosine squared x? It's sine squared, isn't it? And where does that come from? Okay, because remember that stuff I showed you guys on the Pythagorean trig identities? This is huge. This is the one we use the most. Sine squared theta plus cosine squared theta equals 1, right? On the unit circle, what is that? It's just a right triangle with a with a hypotenuse of 1, doesn't it? Like if that's theta, that's 1. Well, what are the coordinates here? If that's theta, my coordinates are cosine theta, sine theta. So I just make a right triangle that looks like that. Well, a squared plus b squared equals c squared, right? So sine squared theta plus cosine squared theta equals 1. If I solve that if I subtract sine squared, I get cosine squared equals 1 minus sine squared. If I subtract cosine squared, I get 1 minus cosine squared equals sine squared, right? So this just becomes then all this stuff just becomes the limit of 5 times sine squared x over 6x squared times 1 plus cosine x, right? Well, look what we can do here now. I've got a sine x over x times a sine x over x, don't I? I didn't mean to make that whole thing purple. I meant to make only that part purple. Let me fix that, just so in the notes you guys can follow this better. Okay, so this part right here, look at this part. What's that? Isn't that just sine x over x times sine x over x, or just sine x over x squared, right? So let's break this limit apart into some pieces. So we've got the limit of 5 over 6 times the quantity 1 plus cosine x times the limit of sine x over x as x approaches 0 squared. Right? Everybody see that? Isn't sine squared x over x squared the same thing as sine x over x, quantity squared? Right? Okay, well, what is that limit? 1 squared is 1. And then if I let x, so we know this part right here just goes to 1 squared is 1. How about over here? If I let x go to 0, doesn't that just give me 5 over 6 times 1 plus 1? Right? So that's, everybody agree? That's just 5 over 12 times 1 equals 5/12. Okay? Because if I let x go to 0, cosine 0 is 1. Yeah. So I get 6 times 1 plus 1. 6 times 2 is 12. Right? Okay? Make sense? And again, that's the reason that one's a bonus at this point is because it involves trig identities and stuff like that, which later in the year, that one probably won't be a bonus. But for now, it is. Okay? All right, what else? Well, I mean, it's just a unit circle issue, right? If I look unit circle, no. Right, there's the point at 0, right? Cosine is the x coordinate, so the cosine of 0, what's this telling us here? It's telling us cosine of 0 equals 1. Sine, well, that's supposed to be a 0, not a theta. Sine of 0 equals 0, right? Remember that, and you can use that, that's this trick, right? If I'm doing this guy, the cosine is going to be square root of 4 over 2. Sine is going to be square root of 0 over 2. Using my little patented hand trick for unit circle. Okay, make sense? It's not mine. That one's, I don't know where I heard that one first. but I stole it. Okay? What else? Okay. Say that again, Rachel. Which one?
Practice test 2, part 1.
Okay.
Question 2.
Okay. Practice test 2, part 1. Question, say it again. Question 2. Okay, yeah, so now this is a super easy one, I would say. Okay, this is one where you get to use technology. Yeah. Yeah, that's literally all you're doing here. So but let's go through that. How could we use technology to solve this for us? So here's what I would recommend. All you need to do, and you get the graphing calculator on the entire second test, right? So let's just make the function f of x equals 12 times the quantity cube root of x minus 1, all divided by x cubed minus 3. X cubed minus 1 as x approaches 1. You got a couple options. You could go over on the graph and just try to find what point it's hitting, but that's not very accurate, is it? Right? You can't really tell what the y value is. We want to round this to what? How many places? The nearest hundredth. So the best thing to do is just put in some values. You can make a table if you want to. That's fine. Or you can even just plug in values. Like what if I pick a value like f of, I want to get very close to 1, right? So f of 0.9999, for example. Okay, what do I get? That. Okay, what if I make that, what if I add an extra 9 to that? Another 9, another 9. What's it approaching? 1.33, isn't it? Right? As I get closer and closer and closer to 1. Now let's do the same thing from the other side just to verify. Let's do 1.01. Okay, but now let's keep adding zeros. If I keep adding zeros, what do you notice? The outputs keep getting closer and closer and closer to 1.33 from the right also. So that's one way we can do it. The other way we could do it is we could just come up here and build a table if we want to, and I could plug values in, right? I could pick values like, let's see, we're approaching 1, so I could go negative 1 point, we're approaching 1 or positive 1, sorry, 0.9991, 0.9992. Just keep going up towards what I'm getting at. You see that's clearly approaching 1.33, and if I keep going on the other side, we can see that as we walk backwards towards 1 from the right, I'm also getting closer and closer and closer to 1.33. Anybody see that? So it's literally just you don't have to do any math on this. You're encouraged to just use technology. Okay? Make sense? Okay? You could potentially, like if you just zoomed in on this thing really far, look, you can see there's actually a bunch of points there. But what if I just get rid of that graph or the table? Right? I could potentially, if I get really, really close here to 1, so I'm focusing in on that point, I could maybe even just take a point and see that as I drag that thing closer and closer, look at the y values. They're getting closer and closer to 1.33. okay? The graph way to me is weaker. I think it's easier to just use a table or just plug in values in a calculator very, very close to 1, okay? Make sense? Good question. What else? Keep going. What do you got? Any other questions? Nothing? Okay. All right. I'm going to pause it then. If you have more questions, keep going. So let's look at this. What happens at 7? Let's take a limit and find out. What is the value, by the way? What is the value? F of 7 is what? 2, right? It's 2. F of 7 is 2. We just need to know what the limit is, if the limit exists, and if so, does the limit agree with that? Okay, so the limit of f of x as x approaches 7 but is not equal to 7, right? That would be this part up here, wouldn't it? Okay. What's that equal to? Well, that's equal to the limit of, I could factor the top, and that's x minus 7 times x plus 7, right? Over x minus 7. Look what happens. Those guys cancel. So if I take my limit, I end up getting 7 plus 7 is 14. So does the limit exist? Yeah, the limit does exist. It's just that the value of the limit is not equal to the value of the function. So the only line that we would choose is the bottom one. The function does exist. The limit does exist. They're just not equal. Okay? I'll do another one of those tomorrow. Yes.